So the second presentation is given by Mr. Tomoki Mizoguchi.
Yes.
From Japan, Kyushu University from Japan. Okay.
Thank you, please. Thank you for your kind introduction, Chairperson, and thank you for coming to my presentation. My name is Tomoki Mizoguchi. I'm a PhD student in Kyushu University. Today I'm going to talk about quantification method for parameters affecting multiscale roughness induced fatigue crack closure. The research about roughness, roughness induced crack closure is most famous. Roughness induced crack closure is one of the most important factors to decide the fatigue crack growth rate. Roughness induced crack closure can be estimated in terms of the geometrical mismatch between fatigue crack surfaces. So if they are mismatching on the surface, the delta K will be decreased. However, the friction effect has not been well discussed. So we focus on two types of roughness that trigger RCC and roughness-induced stress shielding in a trick-marizing steel in a viewpoint of friction. These are two types of multiscale crack roughness. One is the micro-roughness and the other is non-roughness. Micro-roughness is grain size scale roughness, and non-roughness is microstructure roughness. So we attempt to quantify the two-scale fatigue crack roughness of a laminated trick-marizing steel and correlate the quantitative roughness values with the microstructures in a viewpoint of the crack shape. So first of all, I want to introduce about what is trick-marizing steel. The initial laminated microstructure is metastable, as you can see the black part, and marizing multensite, as you can see the gray part. And I want to say one of the important character in this type of trick-marizing steel is it has a laminated structure. And this is the experimental procedure. We carried a tensile fatigue test and finished the fatigue test before fatigue crack propagates by one grain or packet having the same laminar-lime interaction. And on the sample surface, we introduced micro notches by using focused ion beam to achieve a fatigue crack tip in specific grains. And these are SE image of multiscale roughness, but it's too detailed, so I drew a schematics like this, and we set two values to theta micro and theta nano to figure out the region where friction effect has affected. And first, I want to talk about how to calculate theta micro. This is a SE image after fatigue test. This image is raw resolution, so we cannot see the non-roughness. So when calculate theta micro, we won't put these crack shape on the XY coordinate. However, the image having many gradations is difficult to binarize, so I first paint the crack shape like this, and after that we binarize it and trace the crack shape, as you can see the red line, and then put on the XY coordinate like this, and this is the detail. Then we can obtain theta micro. Theta micro could be measured as the slope angle of two adjacent positional data points. Next, I will introduce how to calculate theta nano. This is a schematic of non-roughness, and theta nano can be calculated by using these two values, height of non-roughness and wavelengths of non-roughness. Then you can use just these equations. So first I want to show how to calculate the height of non-roughness. In this study, we obtained the H for 10 images and used the average H value because the H was almost constant as an experimental fact. So we measured the height of non-roughness and sum up it and divided the number of heights. Next, how to calculate the W. W can be calculated by using high-resolution images by dividing the crack lengths by the number of crack diffraction. So for example, in the schematics, the number of diffraction is 1, 2, 3, 4, 5. So the W can be calculated by dividing crack lengths by 5. However, fortunately, in this type of triphomorphism steel, the number of deflection depends on the laminated microstructure. So we don't have to use this high-resolution image. So how to calculate W by using the low-resolution image? W can be calculated by using theta micro and Lx. So first, I want to show you how to calculate Lx. This is a SE image after fatigue test, and this is a prior austenite grain boundary, has the same lambda alignment direction. First, we drew a straight line and count the crossing point between the line and laminated structure. Then we can get two values, the number of crossing points and the length of this line. So we can get Lx by using this equation. So we can calculate W by using this one. So now we have two values. These two values are used to figure out the region affected by the friction stress. So there are two conditions. Theta micro smaller than theta nano and theta micro larger than theta nano. In this condition, theta micro smaller than theta nano condition, during crack opening, the crack surface or contact each other, so it needs more stress to open it. So we focus on the region where friction acted, like this condition. So, for example, these red regions are under this condition. First, we measure these values. These values are projected lengths of the region where theta micro is more than theta nano to the x direction. Then sum up it and divide it by crack length. This is a fraction of the region where friction acted. And this is a new parameter proposed in this study. And next, I will show you the relationship between the microstructure and the fraction of the effective crack surface region for friction. This is the relationship between the lambda alignment direction from the loading direction and the fraction of the region where friction acted. The friction effect was significant, and the lambda alignment was similar to the loading direction. However, this one is relatively small, and the reason is in the thickness of lambda structure. The effect of friction was observed to be small in the thick laminar structure regions, as you can see, this one. Then this is the end of my presentation. In this study, we investigated the relationship between the microstructure and the crack frame friction based on our proposal criterion. Therefore, in future, we will examine the relationship among the proposed criterion, actual friction, and associated crack growth rate. These are conclusion. Thank you for listening.
Thank you very much for this nice presentation.